Today, we're going to dig into the hidden science behind a number you've probably seen 1,000 times but never really thought about: the fat content on a bag of flour. You know the feeling. You're in the grocery store, you pick up a bag of flour, and you glance at the nutrition facts. It says, let's say, 2 grams of fat. But have you ever actually stopped and wondered, how do they know that? I mean, it's not like you can just squeeze flour and get fat out of it, right? Well, the answer is this fascinating bit of chemistry that's been the gold standard for over 100 years. And I'm not kidding, over a century. The official method for this was set up way back in 1922, and it's still the global benchmark. Just think about that for a second. In a world where tech changes every single day, this precise, hands-on chemical process has stayed the undisputed standard.
So, what makes this so tricky in the first place? Well, the main problem is that the fat in flour isn't just hanging out. It's chemically bonded, it's locked up tight with other complex molecules like starches and proteins. It's basically trapped, which makes just measuring it physically completely impossible.
So to get to that fat, you need a key. Not a physical one, but a chemical one. And that powerful chemical key has a name: acid hydrolysis. This is the core process that makes the whole thing work.
So let's dive into part 1. This is all about using that chemical key to basically bust the fat out of its molecular prison.
Okay, so what is acid hydrolysis really? Well, the easiest way to think about it is like a controlled chemical demolition. Scientists use a combination of a strong acid and very specific heat to just snap the bonds holding the flour's structure together. And when that happens, the fat molecules are set free. The whole thing starts with a tiny, super precise 2-gram sample of flour. And here's the first really clever step. They add a little bit of alcohol. Now, this isn't for flavor. It's to moisten the flour particles so they don't clump together. And that's crucial, because if the flour clumps up, the acid can't get to all of it evenly, and your final measurement would be totally wrong. It's one of those small details that makes a huge difference. Then comes the key: the hydrochloric acid. The whole mixture gets heated, stirred, and then cooled down, getting it ready for the next phase.
And when I say heated, this isn't just a casual warming. The procedure is incredibly specific. That water bath has to be kept between 70 and 80 degrees Celsius. It's that level of precise temperature control that makes sure the reaction works just right without accidentally destroying the very fat we're trying to measure.
Okay, so the fat has been unlocked. It's now floating free in that acidic mix, but we still have to figure out a way to get it out of there. And that brings us to part 2, the great ether extraction.
The entire cooled mixture gets transferred into a special piece of lab gear called a Mojonnier flask. It's got this weird tube-balled shape that might look a little funny, but it's actually perfectly designed to let you pour off the top layer of a liquid without messing up the bottom layer, which, as you'll see, is exactly what we need to do. So how do you grab those tiny fat molecules out of the rest of that liquid? Well, you use special solvents, in this case diethyl ether and petroleum ether. The best way to think of them is like powerful fat magnets. Fat absolutely loves to dissolve in them, while most of the other stuff in the mixture doesn't.
And this next part is pure action. The first ether is added and the flask gets shaken, and I mean vigorously, for a full minute. Then the second ether goes in and it gets shaken just as hard for another minute. This isn't some gentle swirl, it's an intense workout, and it's all designed to make sure those ether magnets find and grab onto every single last molecule of fat.
So after all that shaking stops, the mixture is just left to sit for a moment. And this is where the magic happens. Because the ethers are less dense and don't mix with the watery acid layer, they float right to the top. What you're left with is this beautiful, distinct, clear layer. And that top layer? It's now holding all the fat we came here for. So we've captured the fat, but it's still dissolved in all that ether. This final part of the process is maybe the most precise of all, isolating the pure fat by getting to something called constant weight.
The goal here is all about purity. I mean, to get a truly accurate measurement, you have to end up with only the fat, nothing else. That means getting rid of every single last drop of those ether solvents we use to catch it.
So first, that ether fat solution is carefully poured into a beaker that's already been weighed. The ethers are gently evaporated away, usually with a steam bath. Then the beaker, which now just has the fat residue, gets placed into a 100-degree oven to bake off any final tiny traces of solvent or moisture. And finally, it's cooled down and weighed.
But that's the big question, isn't it? I mean, how do you know it's perfectly dry?
If there's even a little bit of solvent left, the weight will be wrong. If it absorbs a little moisture from the air while cooling, the weight will be wrong. So, how do scientists guarantee that level of accuracy?
Well, they do it by reaching what's called constant weight. And this is the definition of meticulous. They repeat the cycle. Dry it in the oven, cool it down, weigh it. Then they do it again. Dry, cool, weigh. They keep doing this over and over until the number on the scale just stops changing. Not by a little bit, not at all. That is how they know with absolute certainty that only pure, dry fat is left. It's the ultimate confirmation.
All right, we've done the chemistry, we've done the extraction, we've done the ridiculously precise drying. Now all that's left is to put it all together and get that final number for the food labor.
You see, accuracy is just everything. The math is pretty simple, actually. You take the final weight of the flask with the dried fat in it, and you subtract the weight of the empty flask you started with. That difference, that's the pure weight of the fat.
So let's imagine that the pure fat from our original 2-gram sample weighs 0.042 grams. A quick calculation, and there it is, 2.1%. That's the number that makes the incredible journey from a lab bench all the way to the packaging you see on the shelf. And the official method itself actually ends with this simple, direct instruction. It's like the final stamp of approval on this long, careful process, making sure that scientists all over the world report their data in the exact same, consistent way.
So there you have it, the whole journey. From a little 2-gram scoop of ordinary flour, through a whole process of chemical keys and fat magnets and intense heat, we get that single, simple number on the nutrition label.
It's pretty amazing to think that this century-old technique is still quietly working behind the scenes, making sure the information we see every day is accurate. It really makes you wonder, doesn't it? What other hidden science is sitting on the shelves of your pantry right now?